Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled More Waves, Boundary Behavior, Snell's Law, and such. And again, I encourage you to be an active learner while watching this video. We concluded the last video by defining the index of refraction, and we'll start this one with repeating that definition. The index of refraction of an optical material, denoted by N, is the ratio of the speed of light in a vacuum, C, which we knew was an upper bound on speeds, and in a vacuum this is a constant, to the speed of light in the material, V. And so N is equal to C divided by V. Now light always travels more slowly in a material than in a vacuum, so the denominator is less than the numerator. So N for any material is always greater than 1. And by definition, N is equal to 1 for a vacuum. Now experimental studies of the directions of the incident, reflected, and refracted waves at an interface or a boundary between optical materials leads to the following conclusion, and this will result in Snell's law. So here are the principles. The incident, reflected, and refracted rays and the normal to the surface all lie in the same plane. That means we can draw a picture because the incident ray, the reflected ray, and the normal ray, and the refracted ray all lie in a plane. So they're all in the same direction, the same piece of paper. So I guess that is number one. Number two, the angle of reflection, theta sub r, is equal to the angle of incidence, theta sub a, for all wavelengths and any pair of substances. So the incident ray comes in, some of it is reflected, some of it continues into this material and is refracted. But the angle of incidence, theta a, is always the same as the angle of reflection. So theta sub r is equal to theta sub a. This relationship, together with the fact that the incident and reflected rays and the normal all lie in the same plane, is called the law of reflection. When a light ray crosses the interface, the boundary, between two substances having different indices of refraction, that means they're different tissues in ultrasound, the trajectory of the ray changes abruptly at the interface. So you see it was going along this direction and it changes abruptly at the interface. The precise manner in which this direction of the ray changes is determined by a mathematical relationship called Snell's law. And so here's what Snell's law says. When a monochromatic, that means it's a single color, light wave, single frequency light ray crosses the interface, the boundary between two given substances, A and B. This is substance A, that's substance B. Then the angles theta A and theta B. So theta A is this one measured to the normal, and this is theta B measured again to the normal, are related to the indices of refraction of A and B by theta, the sine of theta sub A, over the sine of theta sub B is equal to the index of refraction of substance B divided by the index of refraction for substance A. That is going to be called Snell's law. And we'll begin calling it Snell's law here. So here's what we have then, and I will note that sometimes it is easier for students to think about this as being the index of refraction of A times the sine of theta A is equal to the index of refraction of substance B times sine of theta B. And again, these thetas are measured normal to the surface. And here, the A's are on the same side and the B's are on the same side. Here, they are opposite, numerator and denominator. So one of those may be easier to remember than the other. The bending of the ray is always such that the angle on the side with the higher index of refraction is the smaller one. That's the bending, that means the angle. The angles are with respect to the normal to the interface. I've said that a couple times, but that's very important. That's where those angles are measured. And if the ray intersects the interface at a right angle, then there's no bending at all. So you see, if the incident ray intersects the boundary at a 90-degree angle, there is no refraction. If it goes from a material of smaller index of refraction, so NB is less than NA, and this is a substance A, so we're integrating, we're going into one that has less, we're going to be bending away from the normal. So here theta B is going to be bigger than theta A. If we enter a material of larger index of refraction, it bends towards the normal. So here theta B, or not theta B, but the index of refraction of B is bigger than the index of refraction of A, and we hit this this boundary, then it is refracted towards the normal. And here, regardless of the surfaces and regardless of the materials, if it's perpendicular, there's no refraction at all. Snell's law. And when a ray of light approaches the interface from the opposite side, there are again refracted and refracted rays. These two rays, the incident ray and the normal to the surface, again lie in the same plane, and the laws apply just as before. And so the path of a refracted ray is reversible. It's the same from either direction. And the same is true for a reflected ray. The brightness of the refracted and refracted rays depend on the angle of incidence, the two indices of refraction, and the alignment of the field wave with the interface. It's a really kind of an energy kind of thing. Now, most glasses used in optical instruments have index of refraction between 1.5 and 2. A few have larger indices. Diamonds, which are special, have 2.42, and here's one that has even more. It's a titanium dioxide crystalline structure that has 2.62. The index of refraction depends only on the subject, not only on the subject, but also the wavelength. The dependence on wavelength is called dispersion, and that gets discussed. We're not going to go into that. And here is a table, and this is for yellow sodium light. That's the reference frequency. So lambda 0 here is equal to 589 nanometers, and you remember that a nanometer is times 10 to the minus 9th. Now, when light passes from one material to another, the frequency of the wave doesn't change, but the boundary surface cannot create or destroy waves. The number arriving per unit time must equal the number leaving per unit time. Otherwise, incident and transmitted waves couldn't have the definite phase relationship. In any material, V, however, is equal to lambda F. That's one of our fundamental equations. You want to make sure that you remember that for the final exam. Because F is the same in any material and V is always less than the speed of light in a vacuum by a factor of n, lambda is correspondingly reduced. So even though the frequency doesn't change, the wavelength does. And so the wavelength in the material is less than the wavelength in a vacuum by a factor of n. That is, lambda is equal to lambda 0 divided by n. So here's a test your understanding. So here's a figure that we're looking at, and you got a light wave coming in here like this. It's being reflected. It's also being refracted. So it shows a light ray incident on a surface between two media. So here's a left media and there's a right media, I guess. Which path will a ray take along the medium if the ray is leaving a higher index of refraction than the medium the ray is entering. Okay, so the answer is either A, B, or C. Well, if the ray follows path B, then it doesn't refract as it passes from one medium to another. Since the incoming ray comes in at an angle relative to the normal, not normal itself, it's not coming in perpendicularly, it can go out on a path B only if both media have the same index of refraction. Since the ray is traveling from a medium with a higher index into a medium with a lower index, the ray should bend away from the normal. So the correct answer is C. So instead of going to A, it goes C because it's going away. So the answer should have been path C. Here's another problem of a fish pond, and we do have a picture. I'll read it first. Suppose you kneel beside a fish pond in your backyard and look at one of the fish. You see it by the sunlight that reflects off the fish and refracts at an angle to the water-air interface. So you see you're really going this way, where it's coming from the fish. It hits the water at this angle. And notice here's the normal. So it's hitting this at 30 degrees to the normal, but then it is refracted, so it bends and it goes up and your eye is seeing it. And by the way, the fish isn't where you think it is when you're looking at it. So anyway, this is the picture, and we have the index of refraction of water is 1.33. The air is taken to be 1.00. And so you have to figure out, let's see, what do we need to figure out? If the light from the fish to your eye strikes the water at an interface of 60 degrees to the interface. Now this is 60 degrees, but the one that we're really going to be most concerned about is the angle with respect to the normal, so that 30 degrees becomes important. What is the angle of refraction of the air in the air? So it is here. Well, we're just going to use Snell's law, but Snell's law is going to tell us that NB times sine of theta B is equal to NA times sine of theta A, but we wanted to know what the angle was, so we have to do the inverse thing. So Snell's law tells us what I just said, but then I have to do the inverse sine, so I start with this. That's just what I said, but then I'm going to, I have to solve for theta. So first I solve for sine of theta B, and then I take the inverse sine of that. So theta B is equal to the inverse sine of this ratio. This is some algebra. We plug in the numbers, use our calculator, and we get that this is 41.7 degrees. So this theta B is 41.7 degrees. Here's another example. So we have a setup in which two pairs of pins, so here is two pins, and here are two other pins, are separated by a block of glass, and you observe the pins so that the ray reaching your eye passes through all the pins. So you see you're looking like that, and you think that your eye is looking actually through all of the pins. So which of the choices represent the apparent position of the pins on the far side of the glass? So, you know, we have A, B, and C. Well, the actual position of the pins below the glass is B, because it's bent, and you notice that it's bent twice. But the eyes can see only the direction of the ray emerging from the top of the glass. Nothing about the light ray tells you that it was refracted twice as it crosses the two air glass interfaces. Thus, the apparent position of the pins is A. You think it's all lined up. Notice, and again, that's why it's important to read the problems carefully. Notice that the light refracts through the same angle as it crosses from air into glass and from glass into air. And this illustrates the point that we talked about earlier. Let's look at another example. Light rays that enter your eye are affected by the fluid that fills the eyeball. So you've got some fluid here, and that fluid is called the vitreous humor. When red light with a lambda equal 633 nanometers, and this is a helium neon laser, enters your eye, its wavelength drops You see the frequency doesn't change, but the wavelength does. Its frequency drops to this. Use this information to calculate the index of refraction of the fluid and the speed and frequency of the light passing through it. Well, okay, we know from the equation that we just derived a little bit earlier that the index of refraction is the lambda 0 divided by lambda. These two were given. So when I take that ratio, I get that the index of refraction is 1.34, which is very close to being like water. It's very close to what it is for water, but we'll use this number here. So then we know that the velocity is equal to c over n. Actually, we knew that n was c over v, but this is that equation solved for v. Now the speed of light in a vacuum is known to be 3 times 10 to the 8th meters per second. So we divide that by n, and we get that the speed of light in the eye is going to be 2.24 times 10 to the 8th meters per second. And then the frequency is always the velocity divided by lambda, so it's this number divided by that number, and this is the frequency of light, hertz. And there's a practice problem down here if you want to explore that. But again, the frequency doesn't change, but the wavelength does. Okay, here's another example for us to talk. Let's consider a simple reflection problem in which we make use of the fact that the angle of incidence is always equal to the angle of refraction. So two mirrors are perpendicular to each other. So here's mirror 1 down here, and this is mirror 2 that is perpendicular to it. A ray traveling in a plane perpendicular to both mirrors, so you see it's coming, this is the, and in fact this ray is coming along this way, and the ray actually is in a plane that's perpendicular to two of those, is reflected from one mirror and then to the other. So it hits here, bounces off, goes up here, and that bounces off. What is the ray's final direction relative to the original direction? So the original direction was you were coming in at theta 1 from the normal. And what happens here is, well, let's just go through it. So the angle of incidence is equal to the angle of reflection. So this one reflects at theta 1 here. So you see this is a different, because this to this is going to be 2 theta 1 now. But then what happens is this is a right triangle, or this is a 90-degree angle because that's to the normal. So if this is theta 1, this is 90 degrees minus theta 1. And that means that this up here, you see this dotted line is parallel to this mirror. So this is also going to be 90 minus theta 1. And that's the angle that we hit here. But then it's going to be reflected at 90 minus theta 1 at this one as well. And so we're going to be going at, so this is 90 minus theta 1, but this is going to be theta 1 here. So you see what happens is we're being reflected off into the angle that is exactly opposite. This one's coming in at theta 1. This is going out 180 degrees. And so the final direction is opposite to the original direction. Now, the angle of incidence for which the reflected ray emerges can be changed by the incidence. So we're talking about inside this beige medium, we're going up and we're hitting here, and if it's perpendicular, we know there is no refraction at all. If we go here, we see it's reflected that way, but then what happens is we're going to be going at different angles. Now as these angles increase, this changes, and you see this will get bigger and bigger as this one becomes the difference between the two is the same. So because in A in this problem over in B is greater than 1, the sine of theta B is always larger than the sine of theta A, so the ray is going to be bent away from the normal. So it starts being bent away from the normal, and as this one changes, it will be bent more and more away from the normal until it's finally bent this way against the normal. Now Now think about that. What happens here is when it hits this critical angle, it is just reflected tangentially. It never shows up on the other side. And in fact, if you go beyond this critical angle, what will happen is it will be bounced back. It will not emerge on the other side at all because the sign cannot be greater than 1. Okay, so this is called total internal reflection. So when a ray traveling in a material A with index of refraction in sub A reaches an interface or a boundary with a material B having an index in sub B, where in sub B is less than in sub A, it is totally reflected back into material A if the angle of incidence is greater than a critical angle. And the critical angle is determined by the ratio of the indices of refraction. And we can find the critical angle because we set theta B equal 90 and theta B then is 1 in Snell's law. So we get this. The critical angle for internal reflection is the sine of the critical angle of reflection is equal to n sub B over n sub A. And this could be in radians or degrees, but it's going to be an inverse sign because I really wouldn't ask you what the sign is. I'd ask you to find the critical angle. So total internal reflection applies only to light rays that are passing from a greater index into a smaller one. Theta critical is relative to the normal, to the interface, and any ray that has an angle greater than the critical angle is completely reflected. Now, there are applications that take advantage of this, and one of them involves in glass tubes. Because if you design it such these angles are always such that it's totally reflected, you see you'll go with a light ray here, it's totally reflected, it'll be totally reflected, and it keeps getting totally reflected, it's totally contained in here. Now, fiber optic devices like this have found a wide range of medical applications in instruments called endoscopes. And these devices can be inserted directly into the bronchial tubes or other places, knee joints, colons, and so on, for direct visual examination. A bundle of fibers can be enclosed in a hypodermic needle for study of tissues and blood vessels far below the skin. Very small things, but they have this property. In the field where I worked, fiber optics are used in communication systems where we transmit a modulated laser beam. And we will basically turning this thing on and off to be zeros or ones. The number of binary digits that can be transmitted per unit time is proportional to the frequency of the wave, and we can do very high frequencies. Infrared and visible light waves have a much higher frequency than radio waves, so a modulated laser beam can transmit an enormous amount of information through a single fiber optic cable. In fact, we can also do those on different colors, and that's called wavelength division multiplexing, and so this capacity is almost unlimited. Another advantage of fiber optic cables is they are electrical insulators and thus are immune to electrical disturbances and so on and so forth. It really is the technology of the day. Okay, so here is another test of this. So if the upper dielectric, now that's the upper dielectric here, so that's the upper one, we're replaced with one having a higher constant such that NA was less than NB. So NB is up here, NA is down here, and NB is greater. Which of the following rays would be totally reflected internally? And so you have choices of 1, 2, 3, and 4. And so you should study the picture. And the answer is total internal reflection can only occur when a light ray is moving from a higher to a lower. Well, we made this one higher, so that couldn't be true. So the answer is none of them. This is going to be the next low-stakes assessment. We'll post it separately, but I think this is a good problem involving many of the concepts that we've talked about. So you, and this is you, and the height of your eyes above the water is 1.75 meters as it's shown, and you're standing 2 meters from the edge of a 2.5 meter deep swimming pool. And you notice that you can barely see your cell phone, which went missing a few minutes before, at the bottom when you're standing here. So you see your the light reflecting off the cell phone hits the water, is reflected, and then you can see it. How far from the side of the pool is your cell phone? What is this distance down here shown with the question mark? I think that's a good problem tying together much of what we've talked about in this lecture. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.